Hi everyone, welcome to today's coding session. Today I'll be solving binary search problem using Python. I will explain the problem, its constraints, and two approaches, an iterative approach and a recursive approach. As I code, I'll explain each step in detail. Near the end, I will compare time and space complexity analysis. Let's get started. We will be solving the following problem. We are given a sorted array of an integer nums and an integer target. Our task is to search for target in nums. If target exists, we return its index. If target does not exist, we return -1. So example 1, we got num here. Our target is 9. So you can see target does exist inside here. So we're going to return 9 exists and its index 4. Same thing here, num is here, our target is 2. 2 is nowhere to be found here. So we're going to return -1. So there are two options. Either it exists and we return the index, or it doesn't exist and we return -1. Those are the only two options. Now that we understand the problem, let's think about the constraint. An interval could be very short, one interval, or very long, 10,000. All numbers in num are unique. So -10 to the 4th or 10 to the 4th. They're all in ascending order. Since num is already sorted, we can avoid sorting and directly apply binary search. We do not need to modify nums. We only perform index-based comparison to efficiently narrow down the search. Okay, let's implement the iterative approach first using binary search to efficiently find a target in a sorted array. So step 1, we're going to initialize left and right. 0 for the left, and the size of the array -1 to the right. So now we have our left and right boundary for the array. So we won't be going out of bound. Next step, we're going to iterate through the array as long as the left is less than the right, less than or equal to the right. Then this value right here, mid, is what's going to help us find the value we're looking for. And we're going to use left and right in order to do so. So we're going to add left and right. We're going to do integer division and we're going to get 2. And we're going to divide by 2. So if we had, let's say, 5 and we did integer division with 2, that's going to give us 2 instead of 2.5, which is what regular division will give us. So that's why we use the integer division. And if nums at the index mid is equal to target, we're going to return mid. And that's because we found the value. We're saying that the value here is the same as target, so therefore we're going to return the index where the value is located. Else, if nums mid is less than target, in this case, we're going to move our left array to the right. Because basically our number that we're looking for is smaller than the number that we found is smaller than the number we're looking for. So we're going to move our left array to the right so that we shorten the array. And since it's in ascending order, we're moving in the right direction. Now, if the number here is greater than the target, now we want to shorten the array by shortening the right side of the array. So now else is going to shorten the right side of the array by assigning it a smaller value, -1. And then if we cannot find the number that we're looking for, then we return a -1. Okay, so pass both cases, and now let's see how it compares to others. Okay, as you can see, 0 millisecond, and it beats 100% of other solutions. So now let's go through a quick walkthrough. So step 1, we're going to initialize, as I mentioned here. So let's get this smaller. So we're going to initialize left and right, and therefore they're going to be 0, -1. We're going to work with this array, index being a left, right being at 9 in this case. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 element, 0 base index, it would start at 0, 1, 2, all the way up to 9. So now step 2, which we're saying is left less than or equal to the right, and that's the case. 0 is less than 9. So first thing we're going to do is here. So now mid left plus right, which is going to be 9 divided by 2 is going to give us 4, which is the reason we got 4 here. At mid 4 or nums 4, we're going to have the value of 9, and we still have the same indexes, which is here. So we got the 4, mid 4, and now here we're saying, is 9 equal to 7, which is the target value we're looking for? The answer is no. Is 9 less than 7? And the answer is no. So that means we're going to have to go and shorten the array, because we know, since it's in ascending order, that 9 is ahead of 7. So now we're going to shorten the array so that the right is shorter now. Instead of being index 9, it's going to be minus that. Okay, so now we're going to say the smaller, so we're going to minus it as we mentioned. D stays the same. We haven't done anything to the array. And here's where we make the difference, which is when we go back to the loop and we say, is left less than or equal to the right? We already modified it, and it's still the case that the left is less than and equal to the right. So now we're going to, again, assign the new value, add left plus right, which is going to be here. And then it's going to give us index 1, which before we have 4 as the value for mid, and we're going to assign it to right plus 1. In our case here, minus 1, which is going to give us 3. So we got 3 plus 0, and then we're dividing it by 2, which it will give us 1, because 2 only goes 1 into 3 using the floor. So now we got index 1, we got value of 3, which is here, and we're looking for 7. So now that we got here, and we got the smaller value, which is what we're comparing, is 3. So now we're saying, is 3 equal to 7? So that's false. Is 3 less than 7? That's true. So now we're going to shorten the left side in this case. And that's what we get here, where we shorten the left side. And this stays the same, no change. We're still in the same place. And now here's where we do the evaluation. Left plus right, integer division 2, is going to give us index 2, because all we did was increment by 1 our previous array of the left, which before was here. Mid was 1 before. We added 1, and now we're at 2 based on that. So now the value at the mid is 5. And now we go and we start evaluating. Is 5 equal to 7? False. Is 5 less than 7? That's true. So again, we're going to move the left array or the left index to the right in order to shorten it. So we're here now. And now step 7, we know that the target is greater than, so we start searching to the right. So now we got index 2, value is 5. Nothing has changed. This is the same as what we had previously. This is where the change takes place. So mid was 2. We added a 1, and that's going to give us 3. So now we have mid equals 3, left index is 3, and right index is 3. And again, that just happened because we went back to the for loop. Is left less than or equal to the right? And that was true. So when that was the case, now we have mid equals 3, and the value there is 7. So now the only thing the array has is 7. So the last step is we're going to go back here and we're going to say is 7 equal to 7? Yes, it is. So now we're going to return the index. And that's where it says here, return the mid. And in this case, it's going to be 3. Since both of them, the index is 3. And that's the answer for this. So let's write the recursive solution step by step now. So now since we're using the recursive, we're gonna do our first call of the binary search. And we're gonna use self, because when you use a class, you need to use self in order to call another function. So binary search recursive. So the numbers we're going to need, this is the array, then we're going to need the target value, left, which in our case is going to be 0, and the right, which is going to be the length of the array, minus 1. And now we're going to create the function. So it's going to be, let me just copy it. The one distinction here is that we're going to add self, because this is how you declare a function in Python. So we got binary search, num target 0, which in this case we're going to call left, and here we're going to call right. And now if left is greater than right, which means we could not find a value, we're going to return -1, similar to what we did for the previous iterative approach. Then we got mid. This is where we're going to start updating the mid value by adding it to the right and then do an integer division by 2. And here the first thing we want to do is compare. So we got mid, and we're going to see, is it equal to the target value? If it is, we're just going to return mid. If it's not, now we're going to see which direction to go. So if none mid is greater than target, and again, we're in ascending, the array is in ascending order. So if it's greater, if the value that we're looking at is greater, we're going to have to make the right index smaller. So we're going to return, and let's use this again. Actually, since I already used this, let's use this one. Since it has a self, and I don't have to write that. So now we got nums, so the array still, the target, and now this is going to stay the same, but we're going to call it left. So this way it stays the same. And now this right here, since we're trying to make it shorter, so we are currently at a larger value, and we want to make the right side shorter in this case. In order to do so, we just do mid -1. So whatever the mid value we calculated, we subtract 1 from it. And then we do again else. And in this case, what we're saying is whatever number this is less than target. And if that's the case, then we're going to take this. And since here we shorten the right side, instead we're going to shorten the left side. And the way we shorten the left side is by adding 1 to it. And here we just find this, we pass the same value. Okay, so let's see how it works out. See if I got any errors. Okay, so it's accepted for both cases. And let's see how it compares to others. It should be the same as iterative approach. It's just a more eloquent solution. As you can see, 0 millisecond beats 100%, similar to the iterative approach. So let's check out an example, quick example how this one works. So We're going to find the midpoint at index 4 in this case. And just explain the code again. We return here our initial value where we set up the left at 0 and the right at length, let's see, so it's 9. So again, it's the same example. So value 9. And the first thing we see is left greater than right, false, so that we don't do anything here. And now we just are updating 0 plus 9, which is going to give us 4. And that's why we get 4 here. So at index 4, we got 9. So now we're saying is 9 equal to 7? False. Is 9 greater than target, which is 7? And since that's the case, we're going to shorten our right side. Let's see it here. So as we said before, we're going to shorten it here. Nothing is done here, but this is where it takes effect. Where now we got mid, we got, originally it was 4. We subtract the 1, so that gives us 3. So now the right side is going to be a 3, which gives us 0, 1, 2, 3. So this is the right side, we already see here. So now, again, we got mid 1 is going to be value 3. So the question is 3 equal to 7? False. Is 3 greater than 7? False. So now we're going to shorten the left side of the array. And that's how we go here. So is the target greater? No. So that's why we're going mid plus 1. And in this case, mid plus 1 is going to be 2. So we go to the next step. This part, index 2 is 5 now. The value at index 2 is 5. And now we're going to ask the question. Is 5 equal to 7? False. Is 5 greater than 7? False. So again, we're going to increase the left side array, the index of the array. So currently is a 3. So we're going to increase it by 1, so it's going to be 4. So it's currently at 2. We're going to increase it by 1, and it's going to be 3. And when we do that, this is 3 now. So then at 3, we know that we got 7. So it's 7 equal to 7. So now we're going to return the index, which is going to be 3. And that's what we get here. It returns mid. The index is 3. And the value at 3 is 7. And that's how the recursive approach works. So now that we did both the recursive and the iterative approach, let's see how they compare in terms of time and space complexity. So what we got here is the time and space complexity. In the short term, we can see that iterative, which is blue, is slower. But when we're talking about time complexity, we always worry about the worst case scenario. In the worst case scenario, they're both n log n when it comes to time complexity. Where this goes wrong, which is the recursive approach goes wrong, is in regards to space complexity. The iterative approach is always going to be big O of 1. But the iterative approach, the recursive approach, as it goes over 10 to the 5th, it starts growing a lot more. But either way, the recursive approach just takes up more space as it continues to do its recursive steps because it's building up the stack. So both approaches solve the problem with the same big O log n time complexity, but the iterative approach is more memory efficient, big O of 1, because it avoids extra recursive calls. The recursive approach is more elegant and readable, but it consumes big O log n space due to recursive call. This is why iterative method is often preferred for binary search. It maintains efficiency while using constant memory. So to wrap it up, today we unlocked the power of binary search, an efficient way to find a target in a sorted array, iterative approach, fast and memory efficient, O log n time, and O1 space. Recursive approach, elegant but adds extra space overhead, big O of log n space. Iterative is preferred for efficiency while recursion offers readability. So when searching unasserted data, binary search is your best tool, cutting search time exponentially. If you like what I just presented here, please like, subscribe, and stay tuned for more coding insights. See you in the next coding session.